So I'm starting with today's discussion. So we have identified that in case of static fluid, the state of stress at a point was independent of what? It was independent of the orientation of the plane you choose. That is, all planes are principal planes. This was clear to everyone?
Yes,
Because
sir.
on all planes, when it is hydrostatic condition, there are no shear stresses. We know that. Whatever you choose, whichever plane you choose passing through this point P, this will have only normal stresses. So all planes happen to be principal planes. And this is called hydrostatic state of stress. And this is the only special case in which we treat stress as isotropic. That is, it is independent of the orientation of the plane we choose through that point. So this is a very special case. You will never find such a case in case of solids. You will always find such a case in case of fluids at rest. Is that clear? Any doubts to anyone? So this was the stress tensor matrix, and we have noted that there are no shear stresses. So these terms should essentially be equal to 0, and we have put them equal to 0 as far as static fluid is concerned. And these stresses, these are normal stresses, and you know that normal stress will be equal to what? If this point is at height h, what do you think is the stress at this point? This P point is at height h from the free surface. So what do you think is the pressure at this point P? Anyone? What is the pressure at point P? Akash? What?
सर रो जी एच ही आएगा अगर स्टैटिक फ्लूइड है तो.
It is rho gh only, and it will be compressive or it will be tensile.
सर इट वुड बी नन बिकॉज फोर्स हर डायरेक्शन में लग रहा होगा.
But if I say this is a point,
अच्छा,
what do you
यस सर.
think? It should be compressive or tensile? Say this is a point, so pressure will be in all directions.
यस सर, एक कंप्रेसिव
It will be
डायरेक्ट. यस.
compressive, and that's why you have a
माइनस.
negative sign here. Is that clear?
यस.
And all other terms are 0 because we don't have any kind of shear stress on any plane I choose through this point. So all the planes are principal planes, and you are able to see a delta ij here, and delta ij is called the Knocker delta. That is, its value is equal to 1 when I is equal to j, and its value is equal to 0 when I is not equal to j. So I could write down this as a more general case, that is, I take like this. So instead of this, I am putting here, say I have put delta ij, here also delta ij, here also delta ij, here also delta ij. Everywhere delta ij with a p minus pt here. Is this equivalent or not? Is this equivalent or not?
So what is this chromatic delta?
Kronecker delta. Kronecker delta is a operator, or it is something like this. That is, its value is equal to 1 when I is equal to j, and its value is equal to 0 when I is not equal to j. So I could actually write down the entire matrix as like this: minus pt delta ij, minus pt delta ij, minus pt delta ij, minus pt delta ij. I'm putting similar entries on all the entries of the matrix. So this is equivalent to saying what? This. Is this clear to you? Because what do I know? What is ij here for this entry? What is ij? I is equal to x and j is equal to x. What about here? What is I here and what is j here for the second entry?
Y.
I is y, j is x.
Y. X.
So I is not equal to j. So this will turn to 0. So either you could write down in this fashion or in this fashion. Both are equivalent. This is the more general way to do it, because this generalizes the thing, and delta ij, that is the Kronecker delta, will take care itself. You need not remember which is 0, which is non-zero. Delta ij will take care of whether the entry should be 0 or the entry should be non-zero equal to minus pt. Any doubts? So this is the state of stress as far as a fluid at rest is concerned. Now if the fluid is in motion,
डेल्टा क्या होता
क्या कह
है?
रहे हो?
डेल्टा जो लिखा है वो क्या होता है यहाँ पे?
delta ij is called Kronecker delta. This is just a way to represent something, that is delta ij is equal to 1. इसकी वैल्यू 1 हम लिख देते हैं when I is equal to j. हम इसकी वैल्यू लिखते हैं 0 when it is I is not equal to j. This is just a mathematical terminology used for making the equation concise, nothing more than that. So this is the hydrostatic state of stress. So that was the benefit of using delta Ij. So what does that tell you now? Tau Ij is equal to minus Pt delta Ij. So you could represent the entire matrix by only this small equation, because you know that delta Ij will be equal to 1 when I is equal to j, and it will be equal to 0 when I is not equal to j. So this equation is a concise way to write down this equation. Nothing more than that. So wherever this equation appears, you should actually think of this equation as this. This is just another way of representing this matrix, this thing. Is that clear? Any doubts to anyone?
Sir.
Hani. Now I'm coming to stress at a point in a moving fluid. And as of today, we will be treating only laminar flow. So these equations are valid for laminar flow. That should be clear in your mind. That is, all the streamlines, they are in the form of these parallel lines. So these are laminar flow. This represents laminar flow. So what do I see is the state of stress at any point P contains two parts. One part is due to hydrostatic state of stress. In addition to this hydrostatic state of stress, which we have already discussed, there is another stress that is called viscous stress. This is called the static component and this is called the dynamic component. So please remember, whenever fluid is flowing, in addition to this hydrostatic state of stress, at any point, you have additionally viscous state of stress as well. So that the total now becomes equal to static component plus the viscous component. Static or the dynamic contribution or the dynamic. Any doubts to anyone? This represents the viscous stresses. This represents the hydrostatic state of stress. So when the fluid is moving, you have both the components. That is, in addition to hydrostatic state of stress, you have stresses due to viscous forces. Are you clear? Eh? Any doubts? Now, if I ask you, there's a fluid element here, the hydrostatic state of stress, if there was a lone hydrostatic state of stress, what all can this stress do to this fluid element? Can it change its volume? Can hydrostatic state of stress change the volume of the fluid element or not?
नो सर, हमने तो स्टार्टिंग से इनकम्प्रेसिबल मान के रखा है.
हाँ नहीं, अगर मान लीजिए इनकम्प्रेसिबल नहीं आया है, ट्रीटिंग अ जनरल फ्लूइड, in case of gases also there is hydrostatic state of stress.
यस सर, तब तो हो सकता है ना सर.
तब हो सकता है किसी फ्लूइड एलिमेंट में
यस
is जैसे अगर आप, if you think about like this, so there is a tank and you are filling the tank with pressurized air. So what will happen to the fluid element as the tank is filling? The gas is getting compressed.
यस सर.
So please remember, because it is hydrostatic stress is acting in all directions equally, so it has a tendency to change the volume. It will never change the shape, but it will change the volume. For instance, if you have this block and you apply equally in all directions, then its volume can change. But if you apply unequal forces, that is, you apply more force here and less force here, then you know that the shape will also change. So please bear this in mind. Hydrostatic state of stress or hydrostatic stresses can only change the what? Volume of the fluid element.
एक्सक्यूज मी सर.
हाँ जी.
सर ये जो विस्कस स्ट्रेस वाला कंपोनेंट है,
हाँ,
ये सारे नॉर्मल स्ट्रेसेस हैं, शेयर स्ट्रेसेस भी हैं इसके
आप
अंदर?
बताओ इसमें क्या है. सीधा सबस्क्रिप्ट.
सर ये सर वो नॉर्मल और शेयर दोनों ही लिखे
So
हैं.
नॉर्मल ये हो गए और shear, rest of them are shear. So I have pointed out in, I think, the previous lectures that I will be interchangeably using sigma and tau to represent any of the stresses. आपने पता कहां से लगाना है? सिर्फ इन चीजों से. अगर सेम इंडेक्स है then it is normal stress. If it is different index, then it is shear stress. It does not matter whether I am using sigma or I am using tau. Is that clear?
सर
हाँ जी बताइए.
तो आपने यहाँ कहा सर कि सर जब हमारा फ्लूइड सर जो है मूव कर रहा है सर, और यहाँ पे सर हमारे फ्लूइड के जो अपने पॉइंट अज्यूम किया है उसमें
हाँ
सर हाइड्रोस्टैटिक फोर्सेस सर जो है वॉल्यूम हमारा चेंज कर रही है सर. सर ये
हाँ.
कहानी सर स्टैटिक में सर हमें क्यों नहीं दिखी सर?
नहीं, स्टैटिक में भी होगा. अगर स्टैटिक फ्लूइड में यहाँ पे गैस होती, so instead of water there was gas, then also this will change what? The volume.
ओके. तो सर हम नीचे सर जब हम फ्लूइड को लैमिनर फ्लो अज्यूम करेंगे सर, तो क्या सर हम गैसेस भी अज्यूम कर रहे हैं क्या सर साथ में, कि उसके साथ सर गैसेस भी होंगी या दूसरे और कंप्रेसिबल फ्लूइड और होगा?
So we are treating any general fluid and particularly Newtonian fluid. So till now we have not committed whether we are using Newtonian fluid or non-Newtonian fluid, because stress, हमने फोर्स से स्ट्रेस पे आ रहे हैं हम अभी. तो फोर्स से स्ट्रेस में आने में we don't need to make any commitment regarding what is kind of the fluid, what is the property of the fluid. So we are taking in general any compressible or incompressible fluid. So we are taking in general any compressible fluid. If compressibility is low, then this can be treated as incompressible. But we have yet not committed regarding what kind of fluid is it, whether it is Newtonian fluid or non-Newtonian fluid. So this analysis is valid for any fluid which is compressible or incompressible. We have yet not made any clarification regarding whether it is Newtonian or non-Newtonian. It means this equally applies to Newtonian as well as non-Newtonian fluids. And is that clear?
Yes. Thank you, sir.
So viscous stresses. Now think about it. Can you think about viscous stresses are normal stresses? Till now you have been conversant with shear forces. तो जब आप कोई भी आप देखते थे आपको याद होगा कि if this is a plate and fluid is flowing in this direction, you used to see that there will be shear stress on any fluid element which is here. That is, you take like this, you will have some kind of shear stress in this direction. But what about normal viscous stresses?
Excuse me, sir.
हाँ जी.
So this square is a solid obstruction or it's a fluid component, sir?
This thing,
Yes, sir.
this is a fluid element.
Okay.
So I have taken a fluid element, say I draw it like this. So this is the fluid here. Fluid is flowing in right direction. So this blue element I have chosen. So I can actually show the shear stresses on this fluid element. This is tau. What should I write down? Yx. So these were shear stresses. Can you think about normal viscous stresses? Because from Newton's law of viscosity, all of you are much more conversant with this kind of thing. That is, you say shear stress is proportional to rate of change of velocity in y direction. And this is the constant of proportionality. But can you think of viscous stresses also being normal? Have we studied this kind of thing in which normal stresses are also there? That is, I show stresses like this also. I never talked about this, but there will be some stresses in normal direction. Why? And anyone?
Weight of the fluid.
Weight of the fluid, no. Why?
So normal to what direction?
Say I choose this fluid element here.
Okay.
So say this is a fluid element. Say this is A, B, C, D. So what do you know from your knowledge till date? Which faces will have shear stresses?
AB and DC.
AB and DC. So you will study in your solid structures also that there cannot be a single pair. There will be always two pairs. So
Yes,
you will
sir.
have to have like this. So all the faces will have shear stresses. That is one thing. Did you consider any kind of normal stresses on these?
No, sir.
You only considered normal stresses due to which?
Yes, sir.
Pressure force.
But
But you never considered normal forces due to viscous forces.
viscous
But
forces,
but
yes.
what are viscous forces? What is viscous force?
So force due to it is a relative force due to the when only if the fluid is in velocity and motion.
Come to more fundamental definition. What do you mean by viscous force? Force of
Resistance,
cohesion.
cohesion, yeah.
Force of cohesion between similar molecules.
Yes, sir.
Now you have been testing the fluid under shear flow. Shear flow means that this fluid is moving in certain direction and you were testing its viscosity. That is, you were testing the magnitude of force of cohesion. But let me know if these are molecules here. Till now you have been doing like this. That is, you are pulling, or say these molecules are moving in this direction. You suddenly stopped these blue molecules. Due to stopping of these molecules, because the red molecules are in force of attraction with these blue molecules, these will also slow down. That was what you conceived of shear stress. But think about an alternative thing. Say these molecules, instead of stopping this, I was pulling these three molecules in this direction. And say these blue molecules in this direction. Then also there will be some force, resisting force, or not?
Yes. Yes,
Because
sir.
force of cohesion will be in all directions. These are two molecules, they are under force of attraction, so they will actually resist any kind of displacement, whether it is between these two or between these two. So please remember and please remove the misconception that viscous forces or viscous stresses can only be shear in nature. They can both be normal as well as shear. But we always talk about shear because in most of the fluids and most of the flow conditions, normal viscous stresses are negligibly small. That is the only reason we don't talk about normal viscous stresses when we do first 2 or 3 chapters. But this becomes important when you have low velocity or low Reynolds number fluid. For instance, you can try this at home. Try to pour honey on, say, a plate or something like that. What you will see? Say you have honey. What do you expect? Honey will be accelerating with g or some acceleration due to gravity less than g. What do you think? Say this is the column of honey that is coming from this spoon. It is falling down. What do you expect? It will
Less
Less
be
than
than G.
falling down with g or with some other acceleration.
less than G.
Other acceleration that is less than G.
Less than g. Why?
It would
So due to
resist the
the
deformation of
viscous
the.
forces, sir,
So cohesion
between
force
sir.
will be pulling it up.
Yes,
Hmm.
sir.
So this is what you see here that is pulling it up is the normal viscous stress. But if you took water, then this will be nearly G. So that is the normal viscous stresses in case of less viscous liquids. The normal viscous force magnitude is small. So this becomes important when there is low Reynolds number flow, that we will discuss what does low Reynolds number means. As of now, you can conceive of low Reynolds number is that is highly viscous fluid. So that's why when we represent the general framework, we need to have normal viscous stresses also equal non-zero values. So that is why now please be careful. The total state of stress at point P in case of a moving fluid is the sum of hydrostatic state of stress plus stresses due to viscosity. These are called viscous stresses. हाँ जी, clear है? Any doubts to anyone?
Sir,
Hanji.
sir, could you please once again explain that, sir, how normal viscous stresses are applied on fluid elements?
Okay. So this is one example which will help you to understand this. Say you have honey with you. Honey is flowing down. This honey is flowing down. If there were no cohesion force, that is this pull was not there, then this honey should fall with acceleration, with G, with G or not.
Yes, sir. Yes, sir.
But when you calculate its acceleration, it comes out to be less than G. So why it is not accelerating with G? There must be some opposing force acting opposite to the force of gravity.
Gravity.
And that force is called the normal viscous force. Because you know that viscous force is force of cohesion. So please remember, in case of water, mu is small, so you don't practically see this A very different from G. But if you measure A in case of honey, you will experience this fact. Because here normal viscous stresses are significant. They are not negligibly small. Is that clear?
Okay, sir.
So you can conceive of this like this. Say this is a flat plate and now honey is flowing here. Say honey is flowing on the flat plate. So now if you take any fluid element here, what you need to see is there will be what? Shear as well as normal stresses. So in this case, normal stresses will be in which direction? X direction. Because fluid is flowing in this direction.
Yes.
And is that clear?
Yes, sir. Clear, sir. So, sir, in this, so when this fluid is flowing in X direction, sir, any viscous fluid, then we will have, sir, negligible normal viscous forces in this fluid.
Negligible normal forces in?
सर मतलब सर अगर हमारा से हनी से फ्लो कर रहा होगा सर, तो
हाँ,
ऐसे में सर क्योंकि सर ये एक्स डायरेक्शन में फ्लो कर रहा है सर, तो ऐसे में हमें नॉर्मल विस्कस स्ट्रेसेस जीरो मिलेंगी ना सर?
नहीं, नॉर्मल विस्कस स्ट्रेसेस ये तो नॉन जीरो वैल्यूज होंगी.
ओके सर, उसके बावजूद
ये जीरो होगी क्योंकि यहाँ पे तो कुछ फ्लो ही नहीं हो रहा, तो इसको पुल ही नहीं कर रहा.
ओके सर, वाई डायरेक्शन में जीरो होंगी
हाँ,
बट
वाई में जीरो होगा.
ओके सर,
वाई में जीरो होगा क्योंकि यहाँ पे इसको पुल ही नहीं कर रहा. लेकिन मान लो अगर आपके पास एक ग्लास होता, ग्लास में से हनी ओवरफ्लो करके नीचे गिर रहा होता, तो इसमें क्या होगा? अब इसमें से अगर मैं एक फ्लूइड एलिमेंट उठा लूं यहाँ पे, तो उसमें क्या होगा? नॉर्मल स्ट्रेसेस होंगी इस डायरेक्शन में.
यस सर,
और विस्कस स्ट्रेसेस इस डायरेक्शन में. लेकिन नॉर्मल इस डायरेक्शन में नहीं होगी.
ओके सर,
And is that clear now?
यस सर,
So I can have both viscous, normal as well as shear stresses. So that is very important because otherwise you will have a misconception that viscous stresses can only be shear in nature. But they can also have normal component as well. That should be clear in mind. So this is the complete state of stress at a point in case of moving fluid which have both the hydrostatic component and the viscous force component. Are you clear? Now I am coming to the derivation of Navier equation now. Now, this is, say, point P. This is some fluid flowing, and this is point P. So I have assumed a infinitesimally small control volume about this point P, and I have blown this up to show the forces or the stresses acting on this fluid element. Is that clear? So what you know, if you remember, forces are surface and body. What all surface forces are acting? What all surface forces are acting in case of moving fluid? If it is in viscid region, pressure force plus viscous force. What about body force? Body force can have x, y, and z components. That is bx, by, and bz. So you know from Euler equation derivation, if you remember this derivation, you had pressure forces and you had body forces. Now in case of Navier equation, in addition to these two, what all forces you will have? The viscous forces. Is that clear? In addition to pressure force and body force, so this is the pressure force, this is the body force. So this is the surface force, this is the body force. In the surface force, this is the pressure force. In addition to pressure force, I will also have viscous force. And you know that viscous force will have both shear as well as normal components, what we have seen now. So help me write down, what should I write down in case of viscous stresses here or viscous forces? Say these are normal and this is shear. I could have shown this in a single diagram, but for clarity purposes, I have drawn two diagrams. Nothing more than that. Because in the previous case also, although forces were acting at point P only, I showed body force and pressure force on different diagrams just for clarity purposes. So in addition to this, I am now showing the viscous forces. Now what about, this is x direction, what should be here? So this is dx, this is dy, and this is dz. What force will be here? What should I write down? Sigma, what should I write down? First of all, say on this. Say mark, I mark this as AB, wait for a second, AB, this is P, this is C, D, E, F, G. What will be the force or what will be the stress on ABPC? ABPC. What will be the normal stress on ABPC due to viscous effects? Hanj. What will be the normal stress on ABPC due to viscous stresses? Anyone?
Sigma XX.
Sigma XX. So please remember this notation. I am representing the total with tau and due to viscous with sigma. So here I should write down here sigma XX. Sigma XX into what? This is stress. I want to convert this into area. What should I multiply with this?
dx dz.
dy.
Yes sir, dy dz.
And clear hai?
Yes sir.
What about this? PCGF. Sigma YY
into dx dz.
dx dz. And what about BEFP? That is this one. BEFP. Sigma ZZ into dx dy. Any doubts to anyone? So please make it clear. This is very important. Any doubts to anyone of the forces acting on these faces? That is ABPC has sigma XX into dy dz. PF GC has sigma yy into dx dz, and BEFP has sigma zz into dx dy. Now, what about face DEFG? DEFG. What about face DEFG? Try to do it as you did in the case of Euler equation. You had certain force here, a force on at a distant face was equal to what? This force plus some additional force. So with the same token, what should I write down here? For face DEFG, what should be this arrow representing? What should I write down here? Sigma XX plus curly sigma XX by curly X into dx into dy dz. Any doubts to anyone? So ABPC has sigma XX into dy dz, whereas DEFG has sigma XX plus this additional term and everything multiplied by dy dz. I am doing it similar way as I did for surface force when it was only pressure surface force. I did the same thing when I was deriving the Euler equation. So I'm using the same analogy, but now in case of viscous forces, not the pressure forces. Likewise, for face BEDA, what should be this value equal to? Sigma YY plus sigma YY by curly y into dy dx dz. And likewise, I can have for ADGC. So this will be sigma ZZ plus curly sigma ZZ by curly Z into DZ, everything multiplied by dx dy. This is all about normal viscous stresses. But I know that in addition to normal viscous stresses, there are also shear viscous stresses. So what will be this equal to? I will do the same thing. First of all, what will be this equal to? What will be this equal to?
Sigma XY.
I should add tau or I should add sigma?
Sigma.
Please be careful. What should I write down?
Sigma. Sir, sigma xy.
I should write down sigma because I am representing the viscous stresses by sigma and the total stresses by tau. So this should be sigma what?
XY.
X y into dy dz. Clear?
Yes, sir.
What about this? What about this? Sigma xy plus what should I write down? Curly sigma xy by curly x into dx dy dz. Is that clear? Any doubts to anyone?
No,
किसी
sir.
को कोई भी डाउट प्लीज आस्क मी. दिस इज वेरी इंपॉर्टेंट. इफ यू हैव एनी डाउट्स प्लीज आस्क मी. लाइकवाइज हाँ जी बताइए. हाँ जी, एनी डाउट्स? What will be this? What will be this? What will be this value? Sigma
xz
xz into dy tz. And what will be this value? Sigma xz plus curly sigma xz by curly x into dx dy dz. Likewise, I can do for all others as well. So what do I get? If I ask you, say in x direction, which are the forces? What will be your answer? In x direction, sigma xx into dy dz direction towards left plus sigma xx plus curly sigma xx by curly x dx into dy dz direction towards right. What all forces, other forces are in x direction? What all forces are in x direction? This? Anything else? This? Then this one and this one. So what should I write down here? Plus, what should I write down? First of all, what is this force? This force. What is this force? Tau, no, sorry, sigma. What should I write down? Sigma y x into, what should I write down? Sigma yx into
dz dx.
dx dz. What about this force? Sigma yx plus curly sigma yx by curly. What should I put here?
D
Curly
curly ये z.
curly
Sir, वो
यहां से
curly
आप यहां आए हो.
नहीं y
y
curly y yes.
into dy
dy.
everything multiplied by dx dz. These are two forces. What about this force? Say I clean this part and say I ask you regarding this force. What about this force? This is on face this. What about this force? This is sigma what?
sigma
Z
z
x into dy dx. What about this force? Sigma zx plus curly sigma zx by, what should I write down? What should I write down? What should I write down here for this force?
in z ये किसमें
This is in z direction.
z direction.
Curly z dz everything multiplied by dx dy. So I have all forces. So I am writing down here now. There was one force sigma yx into dx dz that was in negative direction, I think. Then sigma yx plus curly sigma yx by curly y dy dx dz. This was in right direction. So I am done with this term. I am done with another term. So I am now left with sigma xy. So I can write down here. So this is sigma, wait for a second. This force was sigma zx, sorry. Sigma zx into dx dy. This is in opposite direction plus sigma zx plus curly sigma zx by curly z dz dx dy. This is in right direction. So under the action of all these forces, the fluid might be accelerating, or if the fluid is moving with constant velocity, then sum of all forces should equal to 0. But this represents actually the x component of the force, viscous force. x component of the viscous force. So it contains all these terms. So you know that these will get cancelled out and you will be only left with, I'm putting here now, in x direction, viscous forces in x direction, they become equal to what? Curly sigma xx by curly x dx dy dz. So I could take this out also, plus sigma yx by curly y plus curly by curly z sigma zx. So this is the surface force in x direction due to viscous effects. And you know that surface force in x direction due to pressure effects was what? If you remember, it was minus, what should I write down? Curly pt by curly x. If you remember, this was the surface force in x direction due to pressure force. And what about body force in x direction? Rho bx, and I should have put here like this. So this is the overall force on any fluid element moving in a fluid or in a moving fluid. These two forces are surface forces and this is the body force. So you are able to see, in addition to this term was in Euler equation, this term was also in Euler equation. So in addition to these two terms, as far as Navier equation is concerned, you have added this term also, and this term is due to viscous forces. So we will continue with this in the next lecture. If you have any doubts, otherwise I will break for today.
Could you please move to the previous slide, sir? Just for a minute.
हाँ जी बताइए. Which one?
सर वो वाली सर जिसमें सर आप कैलकुलेशन कर रहे थे सर.
अच्छा एक सेकंड बस रुक जाइए.
एफएक्स विस्कस फोर्स सर.
दिस इज, हाँ जी ये बताइए. हाँ जी.
ये सर बस इसमें सर एक बार सर बस डायरेक्शन वाला सर देखना था सर, क्या लिखा था ऊपर ऊपर जब आप कैलकुलेशन कर रहे थे सर.
अच्छा ये वाला.
हाँ सर बस याद है सर.
तो ये
सर, इसमें
सिग्मा
एक
एक्स
बार-
एक्स इस डायरेक्शन में, सिग्मा एक्स एक्स प्लस करली सिग्मा इस डायरेक्शन में.
यस सर बिल्कुल.
तो ये हमने पॉजिटिव ले ली, तो ये इसमें से माइनस हो जाएगा.
यस सर.
तो लाइकवाइज सारों में से पॉजिटिव टर्म रह जाएगी.
ओके सर ठीक है सर.
ठीक है ना, क्योंकि प्रेशर में उल्टा होता था, अगर आपको याद हो. देखो
हाँ सर इसका उल्टा
प्रेशर में क्या था, ये इस डायरेक्शन में थी ये वाली टर्म, इसमें से ये माइनस करते थे तो ये इस डायरेक्शन में नेगेटिव आया था. तभी हमारे पास जो सरफेस फोर्स है प्रेशर की वजह से वो क्या है,
नेगेटिव.
नेगेटिव.
तो सर
यहाँ
वहाँ
पे
पे तो इसलिए था ना सर वहाँ पे, क्योंकि सब कुछ कंप्रेसिव था सर.
हाँ
और यहाँ पे
हाँ,
कुछ
that is
टेंसाइल है
there.
सर.
So please remember, in case of pressure forces, you used to show it on a fluid element compressive in nature, like this. यहां से भी कंप्रेस कर रहा है और यहां से भी कंप्रेस कर रहा है. लेकिन जब आप स्ट्रेसेस शो कर रहे हो विस्कस की वजह से, ये दोनों ऑपोजिट हैं, एंड दिस इज टेंसाइल इन इट.
प्रेशर फोर्सेस बेसिकली सर स्टैटिक कंपोनेंट का हिस्सा है क्या सर?
हाँ, प्रेशर फोर्सेस इज ड्यू टू स्टैटिक and viscous forces is due to motion. So when the fluid is moving, in addition to the hydrostatic part, you also have the force due to viscous part. ये तो स्टैटिक में भी थी, सॉरी इसमें नहीं, ये वाली स्टैटिक में थी अकेली. आयलर इक्वेशन में दोनों थी और ये इक्वेशन नहीं थी, क्योंकि उसमें विस्कस रीजन हम लेते नहीं थे. हाँ जी क्लियर है?
Yes sir.
So I will break for today. We will continue with this in the next lecture.
Thank you sir.
Okay then.
Thank you, sir.
Okay.